So on Friday, we started the whole topic on friction, right? And we're just we laid the foundations for understanding friction on Friday. So if you are still a little bit in the dark when it comes to friction, I suggest you go and rewatch those videos, all right, to help you understand what friction is and basically how we calculate it. Right? Just remembering that friction is something that is a change in force, right? Friction can increase as we apply a force on an object, right? Up until it gets to the point where we call it, or we say it's in limiting equilibrium, right? Or another word they like to use is the slipping point. That's the point just before the object is going to move, right? And at this point, we learned that friction takes its maximum value, right? The maximum value being there's some constant of friction, right? Every two surfaces has some coefficient of friction, and it was also directly proportional to the normal contact force. So we take the coefficient of friction and we multiply it by the normal contact force, and that allows us to calculate our friction. Okay? Now, when an object is moving, so in other words, once an object is actually moving, right, we need to remember that friction doesn't just disappear, it obviously remains, and it remains at its maximum value. So if something is in motion, right, we need to remember to account for friction. So having a look at our diagrams over here, we can start with a nice simple horizontal one. Okay, we have an object, right? There can be some force pushing the object in the direction of t, right? Now we need to remember that there is going to be friction, right? So sometimes they will give you a question and they will give you some forces and the weight of the object, and they might not tell you anything about the friction, right? And we need to remember, if we want to calculate the acceleration or anything related to that for the object, we need to take friction into account. And I believe long gone are the days now where they will give you the friction force. So in some of the earlier chapters when we were discussing motion in direction and acceleration, the friction force was given nice and easy. Okay, there's this amount of friction. From now on, you will most likely be required to calculate the friction. So either they're going to give you the coefficient of friction, and then you need to work out the normal contact force and then work out the friction from that, or there will be some other way that you're able to calculate the friction force. But the important thing to remember is that you need to not forget about it, right? You need to remember that friction exists and we need to always account for it. And one of the, like we discussed last week, one of the most difficult things sometimes to remember is we might not know in which direction the friction force applies, okay? And we make an assumption on what we feel the friction might be. And we need to remember that if we get a negative answer, then we've just made the incorrect assumption, and we should just rechange our assumption based on the new information. Okay, so just something to remember. Right, so here we have two examples. We have an object just standing in horizontal surface, right? It can be moving forward, we don't know, right? The direction of motion is indicated and the acceleration direction is indicated. It's always good to state these things, right? Now, when an object is moving up a slope, we usually assume that the direction of motion will be up the line of this slope, right? We call this the line of greatest slope. And most of the time we calculate the acceleration in the same direction, even if it's going to be negative, right? If you imagine something being pushed up a hill, right? And the force pushing the object up the hill is no longer there, the object's going to decelerate. So we could technically calculate the acceleration in the opposite direction, but usually we calculate acceleration in the same as the direction of motion. Right, so what does that mean? Well, that means that if we want to calculate friction, friction is, you'll see there's based on the coefficient and we need also the normal contact force. Right? And we know that friction and the normal contact force are perpendicular to each other. So when we're on a horizontal surface, that's nice and easy. everything's horizontal and vertical usually. But as you see over here, we now have our friction and our normal contact force are no longer horizontal and vertical, right? And so the way that we resolve is slightly different. So here's a simple step-by-step way that you can think about this, okay? In order to calculate the friction, we need to find the normal contact force. So if we're on a horizontal surface, well, that's easy, right? We just need to resolve vertically to find the normal contact force. Usually the only other force in the horizontal or the vertical direction is going to be the weight of the object. So if you have a look over here, to resolve vertically, we would have the normal contact force and the weight of the object. And usually the weight of the object is given, and so we can find the normal contact force. Okay? Once we have the normal contact force, we can use this formula to find the friction. Right? Now that we have the friction, we can resolve horizontally. All right. We need to find horizontal. We'll resolve horizontally to solve for the unknown force, right? The net force that we're after. What direction is the object moving? Right. Because you need to remember that when we want to find acceleration, acceleration is calculated on the net force. Right? This is why we have to resolve both vertically and horizontally to find the direction of the net force. Now, usually when we're talking about friction, you can pretty much assume the direction of motion is either going to be horizontally on a flat surface, or it's going to be up the line of the greatest slope on a hill. We're not really going to worry too much about objects that fly off a hill because the net force is not along the line of greatest slope. Right, if we are trying to find the force, right, this force over here for an object that's on a line of greatest slope, well, we need to resolve perpendicular to that slope, right? And when we resolve perpendicular to the line of greatest slope, well, usually we need to split our weight up into its components, right? We need to take the vertical component in order to resolve for our normal contact force. And again, the whole process is that we need to know what the normal contact force is in order to find the friction force, right? Because they're not really going to give you the friction anymore. They're going to expect you to calculate it. Right? And once we have found the friction force, we can then calculate the force pushing the object either up or down the line of greatest slope. Right? Remember, we can't calculate this force here without knowing the friction force, right? Because the friction force acts in the same line of action. And we don't want to have two unknowns in the same line of action. So we have to solve for one of them. And again, once we're able to find this force, because remember, again, acceleration is calculated on the net force. In other words, the direction that the object is going. And now take this process and remember that we can move and we can work this process backwards, because sometimes we're given the acceleration and we need to work backwards to resolve for something else. And we'll look at two different examples on how that works in a second. Okay, so like I said, sometimes you need to make an assumption, right? They might not give you enough information to determine in which direction friction is going to act, right? So you need to make an assumption in which direction you think the object's going to go, in which direction the object's going to have friction. And then you need to understand that your outcome contradicts your assumption. In other words, if you get a negative answer for friction, then usually you've made the wrong assumption. And all you need to do is change your assumption, right? Change your force diagram quickly and change what you thought was force. So let's just hop straight back into the examples. Right, we have I'm sure, I don't know if any of you have watched curling in the Olympics before. It's one of the most bizarre things where they run with a broom to sweep the ice. Okay, so we have a curling player tries to slide a curling stone of mass 20 kilograms along a horizontal ice rink to stop on top of a target that is 46 meters away from where it was released. Okay. The coefficient of friction between the ice and stone is 0.05, and the player releases the stone with a speed of 6.5 meters per second. They want to know how far this stops from the target. Okay. So this is basically a combination of everything that we've learned now in mechanics, right? Constant acceleration formulas, right? Resolving vertically and horizontally, and now also we have to calculate the friction force. So one of the first things we're going to do is we're going to draw our force diagram, and we're going to make some assumptions about the direction of motion and the acceleration. Okay. So the most obvious force that we have is the weight of the object, right? And that's usually always down. We don't want to get an arrow today. There we go. So we have the vertical weight of the object, right? And that is 20 times the force of gravity, newtons. Right, the next thing we're going to do is we're going to set our direction of motion, because that now will determine in which way we are going to assume the forces are going. So I'm going to say my direction of motion, the direction that this thing's going to run down the ice is from left to right. Right, Kiana, will there be any force applied on the object down the direction of motion? Is there any more force pushing the object down the ice rim?
No.
No, all right, because the initial force that was given to the curling stone is now gone. The player has released it, and so there's actually no more constant force pushing it, right? This basically tells you, or you can kind of work out that our object isn't going to accelerate, it's going to decelerate. However, to make life easier, we're going to keep our acceleration in the same direction as the direction of motion, right? It's just easier to keep everything going in one way. Right, Zara, what force is there going to be that's going to be slowing this object down?
Friction.
Friction. And in which direction will friction usually act?
In the opposite direction.
Right, yeah. So friction usually acts in the opposite direction of motion. So we are going to make an assumption that the friction is acting in this direction. Okay? We're no longer going to call friction F, right? We're going to call friction like that. Right, and Dominic, what other force is there? I'm missing one force. If I have the weight of the object down, remember there's weight down on the surface, there must be an...
Oh, then you've got the contact force of the surface.
There we go, all right? And we can kind of actually not forget about that guy, because we need him, right, to solve for friction, right? Without our normal contact force, in this question, we couldn't find the friction force. Right, so step number one is going to be resolve vertically. We need to resolve vertically to find our normal contact force. Okay, so the two forces acting in the vertical direction, well, the only two forces are the normal contact force, and the force acting in the opposite direction is the weight. Right? And if they're acting in the opposite direction, they must be equal to each other. So we can say that R is equal to 20 G newtons. And you can also change that to 200 if you want. Now we have the normal contact force. Now that we have the normal contact force, we can use it to calculate the friction. Okay, so friction is equal to that coefficient of friction times the normal contact force. And if we go back to the question, we can see that they gave us the normal for the coefficient of friction of 0.05. Right, so 0.05 times by 200. What is that going to be equal to?
Uh, 10.
10. Thank you. Right. Now that we've solved for friction, we can resolve in the horizontal direction to find the net force. That's it. This was resolving vertically. Now we want to resolve horizontally. Right. We also remember that forces perpendicular to the direction of motion, right, don't affect acceleration. So only the horizontal forces here are going to affect our acceleration, although that's what we are assuming. Right, so the only force that I have in this direction is, what is the force going to be, Claire? What's the only force acting in the horizontal direction? Remember, this is not in equilibrium. The object's in motion, it's decelerating. Yeah, the friction is the only. And based on my direction of motion, is this going to be positive 10 newtons or is it going to be negative 10 newtons?
Negative.
Negative, right? Because it's acting in the opposite direction to the direction I've stated as positive, right?
Yeah.
There we go. So there was actually nothing complicated about resolving horizontal. Okay. It's not like when we have equilibrium where one side is equal to the other. When we are resolving something that is accelerating, we need to find the net force. Okay. And this is the force that we will use to find acceleration. Okay. The net force. Remember, right at the very beginning, I kept telling you guys, this is the net force. Okay, we found the net force now, it's minus 10 newtons. The mass of the object is 20 kilograms. All right, sorry, not 2G. And the acceleration is the thing that we're trying to find. Right? And minus 10 divided by 20 is 0.5, I believe. Now you just need to think, okay, does that make sense? I've got a negative answer, negative acceleration, right? The object has been thrown, it's receiving resistance. So in my mind, I'm thinking, okay, yes, the object's going to slow down. Right, now that I have the acceleration, the question has asked us, find how far it stops from its target, okay? So let's list the information that we have. Right? They gave us the initial velocity. Right? The initial velocity is in the direction of motion, so it's positive. We know the final velocity is going to be 0 because after it stops, it's not going to move anymore. And we just calculated the acceleration at minus 0.5 meters per second squared. We want to solve for displacement. So Kiana, which formula will we use if we want to solve for displacement in one go? Well, we'll use that formula because we want to solve for displacement.
Yeah, we don't have time.
Yeah, we have acceleration, we have initial. Remember, we always try to select the formula. We have 5 formulas to choose from, and each formula is one that helps you solve without having to put things into multiple formula, okay? So if we have 3 pieces of information, we can always calculate the 4th piece of information. Right, this is going to be +2 is minus 0.5. And so we'll get displacement of, what's it, 42.25 meters. So the object traveled 42.25 meters, right? So you can see we basically just used all the skills that we've learned in reverse order, right? We've learned now how to calculate friction from the normal contact force, right? So we resolve vertically to find the normal contact force. With that, we're able to calculate the friction, right? With the friction, we can calculate the net horizontal force, which gives us the acceleration, right? And with the acceleration, we can use our constant acceleration formulas to find displacement, right? So it's all the skills that we've now learned building up to calculate problems that we encounter. Right, question B or part B says, in the game there are sweepers. So if you've ever watched curling, there's those guys that skate down the ice in front of the curling stone, and they rub the ice to try and lower the coefficient of friction, right, to make it more smooth, so that curling stone can travel further. Or they roughen it up if they see the thing is going too fast. They'll actually roughen the ice up to slow it down, right? So they're polishing the ice to try and reduce this coefficient of friction. Because remember, the lower the coefficient of friction, the less friction you will have. So they say, assuming they lower the coefficient equally along the entire path, find the reduced coefficient of friction required to get the stone to land on the target. Okay? So we're going to take the problem that we've just dealt with now, and we're going to take it in reverse. Okay? So we still have the same initial velocity. We'll still have the same final velocity, except this time, we don't want our displacement to be 42.25 meters. We want it to be the full 46 meters in order to reach the center of the target. So this time we actually want to calculate what the acceleration would be. What acceleration do we need in order for this object to travel 46 meters? And we'll use exactly the same formula as before. Okay, and we can just solve for S, or sorry, for A, and that should give you also a negative answer, right? And I believe this is rounded to 3 significant figures, 0.459 meters per second, right? Remember to save that in your calculator so that you have the exact answer. Right, now that we have the acceleration, we can calculate what the net force should be. So again, we're just going backwards. So we want to find out what this net force is. Remember, in that Newton's law, this is the net force. Mass times acceleration. This is the force we're trying to calculate. The mass of the object is 20 kilograms, and our velocity is, or sorry, our acceleration is minus 0.459 meters per second squared. Right, that's going to give me a net force of, what's the net force going to be? Somebody with a calculator? Where's my calculator? Sorry, I've lost my calculator, guys. My kids has run off with it.
I think it's negative 9.18.
Yeah.
Okay, sorry about that. I found my calculator. Okay, so that's the net force. Okay, and we saw from the first example that our net force is our friction force. Right? We don't have to resolve vertically again because the contact force hasn't changed. The weight of the object hasn't changed. Right? You could go and resolve vertically again, but it's pointless if you can see that the object hasn't changed weight by some weird thing. Okay. So now that we have the net force, now and this is going to start getting confusing here because we use net force F equal to mass times acceleration, but we also call friction F, right? So just be careful with your forces and your frictions. Okay, that's the net force that you've just calculated there. If I want to calculate friction, we use that formula. And we know that the friction is the net force. And so my total friction must be minus 9.18. Sorry, minus that. So it'll become a positive. And as I said, you could resolve vertically again if you wanted to, but you don't need to. You can work out that your normal contact force has not changed, right? And so solving for, sorry, I keep writing that horribly, right? You can divide that by 200 and get 0.0459 as my coefficient of friction. Okay, so a very nice example showing you everything that you have learned up until this point, all right? It's why we learned how to resolve parallel and perpendicular, why we've learned how to calculate friction, how to calculate friction independent of being told what it is. We know now how to calculate it as long as we have enough information. And then using that information to calculate acceleration or velocity or distance, right? Right, let's have a look at this example as well quickly. We have a woman who drags a box of 20 kilograms up a rough slope. The slope is at an angle at 10 degrees above the horizontal, and the coefficient of friction in the box of the slope is 0.45. The woman pulls the box using a rope held at an angle 20 degrees above the slope, with a tension of 120 newtons. Right? Find whether the force is large enough to create its motion, and if it is, find the acceleration. So I've just drawn a generic diagram here, and we can fill in all the bits of information. So the weight of the object is 20 times the gravitational constant newtons. The friction force we don't know. The normal contact force we don't know. And notice it's perpendicular to the surface, not perpendicular to up and down. The slope is at 10 degrees. And she's pulling this 20 degrees above the line of greatest slope, which is basically the line of the hill. Right? And she's pulling this at 120 newtons. Right, we need to calculate net force, right? Or we need to find out if there is a net force. Except this time it's not a nice vertical problem. We've got many forces, and so we need to look at the forces and decide in which direction to resolve. Okay? We want to find the normal contact force, and in order to do that, we need to resolve perpendicular and, parallel to that direction. So what we're going to have to do is we're going to have to split that 120 newtons into its two components. So this force over here, because it will have both a horizontal and vertical component. And we will also have to split this force because it's also going to have a horizontal and vertical component. My friction force, you can see the friction is acting perpendicular to the normal contact force, And so it will not have a vertical component. So the first step we're going to do is we're going to resolve vertically, right? Remember, we are making the assumption that the box is going to be sliding up and down the hill. And so we are assuming that there's not going to be any, the forces vertically are going to be in equilibrium. So now it's just a matter of finding the forces that are going in the same direction. So we have our normal contact force. And I can see that that 120 newtons is going to have a vertical component going in the same direction, right? And that vertical component should be 120. The vertical component will be adjacent to that, so it'll be sine 20. Right, so this, I'm working out this force over here. And then I need to go look down at the bottom, and I can see I have a vertical component from the weight, right, acting in the opposite direction. So this will be 200 because it's 20 times 10. And I want to work out the vertical component of that force. That looks like it's going to be cos of 10 degrees. Right, and here we can just solve for the normal contact. So we'll take 200 cos 10 minus 120 sine 20, and we get 155.919, which we can round to three significant figures of 156. But keep the original answer in your calculator, right? Because we're going to use that to calculate everything else now. Right, we've found the normal contact force. So the next thing to do is find the friction force. We've got the coefficient of friction, and so we can use our answer to calculate friction. So we had a coefficient of 0.45 multiplied by this 156. Now, obviously, don't use 156. Use the answer in your calculator. I still have the answer in my calculator, so I'm going to immediately multiply by 0.45. And that will give me 70.1636, etc. newtons, okay, which we can approximate to 70.2 newtons, right? But again, keeping the original answer in your calculator. Right, if it's friction, I would store this friction force. You've got a nice colorful red button on your calculator for the letter F. Store it in F if that helps you remember. Right, now what we need to do is we need to work out if there is any net force. Is this box actually going to move? Right, and so what we can do is we can resolve horizontally and see what force we get. And so we're going to look at the forces acting in opposite directions and see which side might be of a greater force. Okay, again, remember we are assuming that the direction of motion is up the hill, and we need to remember that if we get a negative answer, because maybe we might not get what we assumed. So the force is acting up the hill. The only force acting up the hill is that 120 Newton, but now we want the horizontal component of that force. That's going to give you cos of 10 degrees. Right, now we're going to add the forces in the other direction. But remember, when they're in the opposite direction, it's actually a negative force. So we have minus, right? Well, we know the friction force of 70.2 newtons. And the other force acting in that direction is this horizontal component of the weight here. So that will be 200 sine 10 degrees. So let's see what we get. We go 120 cos 10 degrees minus 200 sine 10 degrees. Right? I still happen to have my friction force in my calculator, so I'm going to subtract the answer, and I get a net force of 13.283, etc. newtons, right? That tells me that there is a positive net force. In other words, the force is going in the direction of motion. So what you've calculated here, this is your net force, right? And sign matters. If it's negative, that means that the net force was in the opposite direction to the direction that you thought it was going to be. Right, very quickly, force equal mass times acceleration, right? We know the force now, it's 13.283. The mass of the object was 20 kilograms. So we can divide our answer by 20. And I've done something horrendously wrong, I think, in my calculator and got the wrong answer. Or is that right? That's right. So there we go. So again, resolve vertically, find your normal contact force, use the coefficient of friction to find the friction force, resolve horizontally to find the net force, and you can use it to calculate acceleration.